Thanks everybody for joining today. Tim Blasius, I work for Magnaflux, Chemical Product Manager for North America. We're going to talk about why particle size doesn't matter, which I'm going to admit right now is a bit of a clickbaiting title, but it got you all in the room, so here we are. So just a little bit of an overview of what we're going to talk about today. A little bit of background on how fluorescent magnetic particles actually are made, just a base on everybody. We'll talk about some factors that influence the performance of those particles, and then we'll talk about the testing that we did, and talk about the title of the presentation, answer the question about whether particle size really matters at the end of the day. Just everyone hold your questions for the end, just to clarify that, and we'll cover them at the very end. All right, so simplified process of how magnetic particles are made, particularly fluorescent magnetic particles. It's really a combination of three different things. You have iron powder to make it magnetic, you have fluorescent pigment to give it that nice bright color, and then you have resin to bind everything together. So there's a process to adhere all that together, and you end up with a particle at the end of the day. So this is a very simplified version, right? And everyone's got a different proprietary way that they do it, but that's kind of generally how it all works. And you can control that process and come out with different particle sizes, distributions, different aspects of the particle, that all influence the performance at the end of the day. A little bit how they work and the theory behind them, because I think it's important to understand this. The process for using magnetic particles, you magnetize the surface of the part, you apply the particles, those particles accumulate in leakage fields, you observe and evaluate and record those leakage field indications, and then you may demagnetize the part. So this image over here on the left helps kind of explain some of that. So you can see the magnetic field over here running left to right. And this is a ferromagnetic part surface. And you can see here there's an indication or a disruption in that magnetic part surface, which creates the leakage field in the magnetic field, and that pulls these green little particles here into place. Now the reason why we did some of this work is we're having conversations with some customers and end users who were requesting very small particle sizes. So 2 and 3 micron average particle size for their magnetic particles they were looking for. And we were curious why that was. We didn't make a particle that was that small, so we were thinking, do we need to come out with a particle that's smaller? Let's do some work on this and see if this is really an important thing. What we think was going on is we think there may have been some misconceptions about how these particles were actually functioning. We think that maybe some people were getting confused between mag particle and fluorescent penetrant. So if you think about fluorescent penetrant, particularly with the surface indication here, for penetrant, you have to have that penetrant go inside of the little crack there, right? That's not the case for mag particle. The particles don't actually go inside of the crack. They kind of float on top of the surface of the part. So those particles don't necessarily need to fit inside of the crack in order to form an indication. The leakage field just pulls those particles together. They don't actually go inside of that crack. The other thing to note here is this is clearly a surface indication. Mag particle can be used for slightly subsurface indications as well. So another thing to think about there. So we think that's where some of the maybe confusion or misconception about particle size and how it influences performance is coming from. But we really wanted to do some testing to prove out whether that was the case or not.
Now, there's a lot of other pieces to a magnetic particle that are important for its performance that are not necessarily related to particle size or how that particle is constructed. One of those things is brightness and background. So a good example of that is on the left. On the left side of that left image, you have a very bright background. And even though the indication is quite bright, it doesn't show up very well against that bright background. On the right side of that image, we see a much darker background with that same brightness of indication. And you can see very clearly that indication shows up quite well. So this is an important thing to consider when you're looking at magnetic particles. Not only the brightness of the indication itself, but also the lack of brightness or the lack of background that comes in the surrounding space around that indication. And you get this by choosing the right carrier fluid, as well as making sure that your mag particles are of a good structure, that they don't break down and release fluorescent material into the carrier fluid and into your background. On the right-hand side is an example of how color contrast becomes important. So not only brightness and background, but also how that color interacts with the other colors around it can be really important in seeing your indications very easily as an operator. This is a bit of an optical illusion on the right-hand side. You can see the kind of green swirls going through the image. And you can see that they appear to change color as they go from top left to bottom left and then down to bottom right. In fact, the kind of green to blues transition there doesn't actually occur. So those green lines are actually green all the way around the swirl. But what happens is the colors around those green lines change. And when they change, your eye perceives that color to be different, even though it's actually not. So this is an example of how the kind of surrounding color around an indication may change the way that your eye perceives it and how much that indication really stands out to you. This is another aspect of this is the yellow versus bluish color to it. So when you have a very yellow kind of surrounding area, or even just a yellow indication in general, that stands out more to your eye. It allows your eye to pick up that green color really well. When you have a more bluish kind of surrounding color or bluish indication, the indication doesn't pop as much to your eye, and you get some of this kind of color blending that goes on, which just has to do with the way that your eye actually perceives color. Your eye perceives color much less finely than it does just general light. So you get this sort of blending action that occurs when you have a lot of different colors put next to each other. So that's another factor as well, that this kind of bluish color or having that color around your indications can cause some blending of colors to happen within your eye itself. So those are some things that are important for performance. Additional factors, your particle size is definitely important, but it's just one component of all different factors that go into making a very strong performing particle. Particle composition, so the ability of your particle to stay together, to come together in the right levels with your iron versus your fluorescent pigment. As well as your durability. So how long can that particle stay together and not release pigment into the background and create a lot of extra background going on within your mag particle solution. Particle brightness and contrast we talked about in the previous section, so that's a really big factor, as well as the particle size distribution. So when we reference particle size here, we are often talking about the mean or the average particle size. And in fact, no magnetic particle exists at only one single mean particle size. Any magnetic particle kind of bundle that you have has actually a wide range of particle sizes in it. And so depending on how wide or tight that range is, can have different effects on how that particle performs. Additionally, I mentioned this a bit earlier, but what type of carrier you select, whether it's NDT, an NDT developed carrier, or if it's kind of just any other oil, that can have an impact on how your particle actually performs as well. One thing to cover here is just the size of a micron, and just to kind of give people some example of how small that really is. So the left image, I think, is a good example of the kind of big piece of something that you see is actually a human hair, and that's 70 microns. The filament that's laying on top of that human hair is 6 microns. When we're talking about most of the magnetic particles, they range around 2 microns to 19 microns in mean particle size. And so we're talking about very small particles already, and the differences between those particle sizes are actually also really, really small. And that, I think, gives you kind of a good example of just how fine of precision we're talking about when we're talking about these differences in particle size. All right, so back to our hypothesis. I talked a little bit about the misconceptions that we are seeing a little bit in the market, that smaller particle sizes were necessary in order to get better performing products, namely that smaller size particles allow you to see smaller indications better. And so our hypothesis going into our testing was that particle size is predictive of performance for these fluorescent magnetic particles, and that smaller particles are better. So in order to test this, we conducted testing on both a tool steel ring and a Floptech gear with known flaws. We used the same setup procedure for all of the products that we used, and we counted how many visible indications there were on the tool steel ring. And then we also looked at 2 specific indication areas on the Floptech gear. And we'll talk about both of those sets of data. And what we found is that particle size is not predictive of performance for these fluorescent magnetic particles that we tested. And also that smaller particles are not necessarily better. Just a little bit about our setup. So I mentioned our team in DeWitt, Iowa. We have a great R&D team out there that did a lot of this work. We tested 11 different magnetic particle suspensions across 7 manufacturers. So really tried to get some of the top magnetic particle options that are out there globally. We had a mean particle size that ranged between 2 and 19 microns. So some of these mag particles claim to be very small in particle size. Some of them claim to be very large in particle size. We focused on claimed particle size per what was on their product data sheets or available on websites and things like that, which I think is an important factor that we'll talk a little bit about later. We use an ASTM 1444 conforming standard practice for testing these magnetic particles on the tool steel ring at 2500 amps. And we used a fixed UV light source for all of our imaging to make sure that we were being consistent across. So here's an example of our 6 micron particle versus a 3 micron particle, as well as 6 micron versus 2 micron. So this gives you kind of a mid-range particle size product versus a couple of very small particle size products. And I'll focus on the image on the left for now. So here we can see the 6 micron particle showed 9 indications, whereas the 3 micron only showed 8 indications. Additionally, that image shows just a lot of background on the 3 micron particle, a lot more than the 6 micron particle. So that background actually shows up kind of bluish in color. So think back to what I was talking about earlier about the brightness in background and the color contrast. It really kind of blurs out those indications. So even though you may be able to see them, they're not as easy to pick up as the product on the left that has those 9 indications. So that's another factor for operators to consider when they're looking at different particle options. The image on the right shows a 6 micron particle versus a 2 micron. And again, we have the 6 micron particle performing better, showing more indications than the smaller 2 micron particle. This also has a little bit of a bluish tint to it, not quite as extreme as the 3 micron particle, but still a factor, still a bit more background showing up with that 2 micron. On the image on the left on this one, we've got a 4 micron versus a 7 micron particle. And here we've got the 4 micron showing 8 indications and the 7 showing 7 indications. So this is a case where a smaller particle is slightly better. Additionally, that 7 micron particle seems to be showing some de-wetting going on or some blurred background on that right side of that image. Here on the right-hand side, we've got a 6 micron versus a 12 micron. So this one, the 12 micron, quite a bit larger in particle size. And actually smaller and a fewer number of indications showing up. Additionally, this one also shows some of that de-wetting happening on the right-hand side of that image. So this is an example chart. If our hypothesis was true, what would that data look like? On the y-axis, we have sensitivity. On the x-axis, we have particle size. Sensitivity we measure by number of indications on a tool steel ring. And again, the particle size is the average mean particle size. So if our hypothesis was true that smaller particles perform better, this is what we would expect to see. Upper left going down to the lower right in the chart, and those dots kind of following around a consistent line or path. In reality, this is what we see. So we do have a little bit of top left to bottom right showing, which would indicate that smaller is maybe slightly better. The problem we have is that these points don't really follow any sort of line or linear format. You can see that from the R squared in the top. The R squared value is 0.05, which is quite low. The way we try to understand R squared, if R squared is equal to 1, that's a perfect correlation or relationship. That would suggest that 100% of the variation in sensitivity is determined by the variation in particle size. When we have 0.05, that tells us that only 5% of the variation in sensitivity is determined by the variation in particle size. Namely that particle size doesn't really influence performance very much versus the rest of the other items that are out there. So this is pretty interesting data, but I think you could argue that maybe there's some outliers on the far right there and maybe skewing some of the data there. So we did remove those 2 outliers and take a look at what that looks like. And you can see that it does improve the R squared value. So the correlation does improve. So now 26% of the variation in sensitivity is determined by the variation in particle size. So still not, a significant amount, but it's definitely more than it was before. So there is some relationship there. The problem we have now is that it's no longer smaller is better. So you notice that the lines shifted from being top left to bottom right to now going from bottom left to top right. And what that tells us then is that actually in this kind of data set that we've got and remove these larger outliers, actually a little bit larger particle size performs better. I mentioned earlier that we were comparing things to claimed particle size. So what particle size was actually listed on the PDS or the website for a particular product. We recognize that you can measure particle size in a number of different ways. And so not everyone, perhaps it's possible that not everyone measures particle size using the exact same methodology. And that might be throwing some of our data off. So we wanted to test that by running those particles through a single source of data in terms of what that particle size actually looks like. So we used a Hariba diffraction particle size analyzer, laser diffraction particle size analyzer, to actually calculate what the particle size was for each of those products. And we plotted that against the sensitivity. And this is what we got. It's really still telling us that there's not a correlation really between sensitivity and particle size with the products that we tested. So again, a 0.015 R squared, very small amount of predictability between sensitivity and particle size. So we did all that testing on a tool seal ring. Now we recognize that a tool seal ring may not be representative of some of the different market segments that are out there. Specifically, the tool seal ring shows subsurface indications. So the holes are drilled underneath the surface of that part and the testing is done on the surface. We wanted to test a part that showed some surface defects, some cracks that are actually open to the surface. And that's a little bit relating, I think, to some of the misconception idea that we had about why people are thinking about smaller particles being better, and that misconception or confusion with how penetrant works versus how mag particle works. So we wanted to test this out on a part with surface indications. We conducted all the testing using the same setup between the different products. 800 amps we used on this Flawtech machine gear has 2 known surface defects that are indicated on the image on the right. And the results that we found is that smaller particle size products don't necessarily translate to better indications or better performance. And we'll specifically focus on the indication on the far right, which I'll reference as the small indication. So here we've got an example of a 6 micron particle versus a 3 micron particle. The 6 micron on the left shows up both indications very clearly, not a lot of background. Those indications show up quite well. On the 3 micron particle, the main indication, or the larger indication, shows up pretty decently. However, the small indication is very difficult to see. Additionally, there's some other kind of false indications, I'll call them, or different spotting in there that's happening with that 3 micron particle. So here, clearly, the larger particle is performing better. And on this one, we've got a 2 micron versus a 12 micron particle. So here on the 2 micron, you can see again the large indication shows up quite well. The small indication, a little bit blurred out by some background, has some bluish color to it as well that might be causing some of that blurring. On the 12 micron particle, on the other hand, both indications show up quite well. So here again, we've got a larger particle performing better, showing smaller indications better, even with a surface indication part. And one more here, we've got a 4 micron versus a 7 micron particle. So the 4 micron shows up the main indication, or sorry, the large indication quite well. But again, the small indication is visible, but a little bit difficult to see. Here on the 7 micron particle, we've got a pretty decent large indication. I think there's a little bit of blurring going on with the imaging. I don't think that's actually how it shows up to the naked eye, but a little bit of blurring there, but I think it's probably more the image itself. And then the small indication actually shows up really well with this image. So again, here's this larger particle performing better than the smaller particle. So all in all, when we did the tool steel ring testing as well as this Flawtech gear testing, what we found is that particle size by itself does not predict performance of fluorescent magnetic particles, and specifically smaller is not necessarily better when you're looking at magnetic particles. So if particle size isn't the thing to look at, then what do I care about? What do I want to care about when I'm looking at evaluating different fluorescent magnetic particles? Well, the key that you want to look for is something that's very highly sensitive, strongly ferromagnetic, and something that will be easily moved into leakage fields. So we talked earlier about how magnetic particles actually function. It's all about being captured by that leakage field and the forces around it. So if you have a particle that interacts well and moves well to find those leakage fields, that's going to be a strong performing particle. Particle size is important to control and really make sure that it's in the right range and that the distribution is good as well. And it's mostly about enabling particle mobility and forming the indications well. It's not necessarily about finding a particle that's small enough to fit into the cracks, quote. Clear, bright indications are really important, and that comes from having a bright indication, but also having a very not bright background. So you want to minimize the amount of background around your indications and really have bright indications that show up well, but don't get kind of blurred out by the other things going on in the mag particle solution. We talked about durability as well. So you want to have a particle that is well structured, but also maintains its structure over time so that you don't have a lot of fluorescence leaking into your background and creating a lot of background fluorescence going on within your evaluations. And then carrier fluid is important as well. So we talked a lot about particles today, but having an NDT approved carrier fluid that allows for good mobility, but also minimizes background can be really helpful in delivering a strong performing particle. And this all kind of comes with a caveat of it all depends on the application at the end of the day. Some smooth parts might perform differently with different particles than rough parts. If you've got a potential issue with corrosion or particle degradation where you're really beating the particles up a lot in your process, that could be something you want to factor in as well when you're looking at selecting the right particle. Additionally, the amount of visible light that's in your inspection area can be important. If you get a really, really dark room, maybe you don't need quite as much brightness coming from your particles and you're able to see things pretty easily. If you have a lot of visible light that might be getting in the way, maybe you need a much brighter particle that'll show up really well when that leakage of visible light comes through. So these are all important factors to consider when you're looking at mag particles and trying to find the right one for your particular application. We always recommend that testing on your parts in your particular application situation is the best way to confirm which is the right particle for you.